Ladies and gentlemen, please welcome our next speaker, Markus Ziller, presenting the topic, From Monolith to Microservices with the Strangler Pattern.
All right. Hi, everyone. My name is Markus Ziller. I'm a solutions architect at Amazon Web Services. And as a solutions architect at AWS, I help my customers solve their business challenges using AWS technology. And in recent years, one of the biggest challenges that my customers face is the modernization of their existing applications. And this quite often includes going from their monolithic systems towards a microservice-based architecture. So today I want to talk about the Strangler Pattern, which is a tried and tested way of approaching such a transition. But before I dive deep into the pattern and discuss its ins and outs, I want to take a step back and zoom out a bit and discuss why this is happening, why we see this happening in all industries. And at the end of the day, it comes down to the fact that the playing field has been leveled. Cloud computing, open source solutions, services, they really democratized the access to state-of-the-art technology. And that removed the entry barriers into many industries, into many markets, and made it easier for new startups to challenge the status quo. And that's something we see across all industries, that the old ways of doing things, they get challenged by new ways of thinking. Before I joined AWS, I worked in the media industry, and I witnessed firsthand the disruptive power of the video streaming services that were coming up, services that were born in the cloud. And that is happening across all the industries. And the only thing that allows established companies to stay ahead of the curve is the ability to adapt and to innovate on themselves. And in order to be able to do that, you need a solid technological foundation. So it is not surprising that for most customers, app modernization is a key theme in everything they do. And they look to the cloud as an enabler to do exactly that. Customers migrate to the cloud for a large number of reasons, but two of them are always high up the list. One is cost, and the other is the ability to innovate. Every customer wants to be cost efficient, and every customer wants to be more innovative, to drive new features, to deliver new products at a faster pace. And if we look at a typical cloud journey, I mean, every cloud journey is a bit different, every modernization journey is different, but there's a pattern that we see, and that is that we start off on-prem. So these are companies that have been doing IT for decades, and they started off in a data center because there was nothing else there. But at some point, the business really outgrew what the data center was capable of delivering. That's when they look to the cloud. And most often, this happens in a lift and shift fashion. So what they do is they take all they have on-prem, one by one, all the applications, all the tools, all the scripts, all they built over the last decades, and move it to the cloud, move it to AWS just as is. And that is an important first step, but it only gets you so far. The gains that you get are comparably little. So what then comes next is the phase of optimization. That's where customers really are now in the cloud, and they try to maximize the efficiency of what they are running in the cloud without changing the architecture itself. That includes things like right-sizing instances. So find the right instance size for your workloads. Going from self-managed databases to managed databases, for instance, using Amazon RES, or relational database service. And that gets them already quite far. But after you've done all the optimizations, you reach a point where you get diminishing returns, where the return on invest is just not given anymore. So if you want to go even further, you need to more embrace the cloud and go into the modernization phase. That's where we really think about how can we utilize what we have in the best way. And that includes things like leaning heavily on serverless, doing DevOps, whatever that might mean for you, but it's just the idea of doing it. And that's where the existing applications start to get in the way, because it's really hard to do serverless with a monolith that has like 1 million lines of code. That is just not working out well. And that's where customers think about, okay, what can we do? How can we get from this point where we are now to this point where we want to be? And in order to better understand like the position they are in, it's important to understand what is a monolith. How is it more or less defined? So when you have a monolith, by definition, you have a single code base. Everything that application does is within one code base. All the features are in that code, and that makes it tightly coupled. So it's hard to separate those. You share resources, so you have a database, mostly SQL, but you also share things like CPU, memory, and so on. If you want to deploy the thing, that's monolithic. So regardless if you have a small change or a large change, you need to build and deploy the entire thing. If you want to scale the thing because your traffic pattern changes, this is most of the time then done vertically. So you add a bigger machine to be able to serve more traffic. Sometimes you can scale horizontally a bit, but usually that's not happening. You're locked into a single technology stack. So if you started your monolith in COBOL 30 years ago, that's what you're stuck with, and that is not a very pleasant place to be. With many dependencies and then a large code base, that leads to longer build times because you need to compile, build, bundle, test all that code every time you deploy, which can cause a problem. And lastly, since everything is running in one machine, regardless of how clean you build your code, it's still running on one physical machine. And if that machine, this virtual machine, is having a bad day, the entire thing goes down. From an architecture perspective, more or less looks like this. I mean, there's a bit of nuance, but 99% of the monolith look a bit like this. So there's a database. Most of the time it's an SQL database. Then you have the monolith that is running on an EC2, a virtual machine or wherever with all the components in it. There's some ingress, sometimes a load balancer, sometimes you have an Nginx running, or sometimes you connect directly to the machine. That's more or less how a monolith look like. You've all seen that. In contrast, when we look at microservices, they are by design, that's one of the characteristics of microservices, they're decomposed. So you take the functionality and decompose it. That creates a loose coupling between independent pieces of your architecture. Each of those pieces solves a specific problem, and you can, on the one hand, deploy them independently, but you can also develop them independently. You don't not stuck to COBOL anymore. You can now use Python or Java or whatever you prefer. It also comes with a decentralized data management because, again, by design, in a microservice architecture, you don't share state. Every microservice owns their own data, their own persistence layer, and you need to find ways to centralize this because at the end of the day, you're going to need all the data. Same goes for network communication. You now need to have means to discover services and communicate via the network. It provides better degree of fault isolation, so if the machine of microservice A goes down, it doesn't affect the machine of microservice B. There might still be interdependencies that you need to manage. And scaling is horizontally, so you just add more containers, more virtual machines if you need to scale with the increased demand. In terms of architecture, again, 99%, maybe 95% of the microservice architectures fall in that category, look like this. So you have an ingress or some load balancer that redirects traffic to some microservices. They have a specific task. They communicate among each other synchronously, asynchronously, doesn't really matter. And they all have a persistence layer, which they own and only they own. And what we can consider this is two ends of a spectrum. So it's not either microservice or monolith. It's really a spectrum. And our job as developers, architects, whatever your role is really to find the sweet spot on that spectrum to understand what is the right design for your workload. And that's where things sometimes go wrong. So we are all builders. You wouldn't join a session about the Strangler Pattern if you're not a builder, if you don't enjoy solving interesting technological challenges. And that is a great thing, but that often leads us to make biased decisions. And the thing is, There are good reasons and there are bad reasons to do microservices, and unfortunately I've seen a couple of attempts to do microservices fail because they were started for the wrong reasons. I don't want to dive too deep into all the reasons to do or not do microservices. I just want to give a few of the reasons that I think are bad reasons or good reasons that I saw in the past. So I sometimes hear the sentiment that monoliths are per se bad or slow or inefficient, and that is not at all true. Well-designed monolithic application with a moderately sized database can handle a frightening number of requests per second. So if performance is all you care about, Monolith might be well the thing that you want to have for your workload. That's just how it's done today. Also not really true. There's a lot of buzz in that area and many companies are doing this and are vocal about this, but there are plenty of high functioning monoliths or services would be considered a monolith that just continue to work and there's no need to change them. Another argument I sometimes hear is Amazon is doing it too, or Facebook is doing it too. That is true, but Amazon literally has tens of thousands of developers building applications. And if you're at that kind of scale, you don't have many options to manage the complexity. Microservices are easier. I can guarantee you they are not easier. Microservices are actually really hard to do well because you need to manage a lot of distributed complexity and it's a really hard thing to do right. And lastly, it's the idea that it will make scaling much easier when you get to number X or number Y, which is probably true, but I'd argue focus your energy on getting to that number. Build your systems in a way that you can then easily decompose, but don't optimize from the start. I often see this with startups to optimize from the start, and they're never going to reach that number. But that being said, there are also quite good reasons to do microservices. So one of the good reasons is if the business wants to move faster but can't because the backend is holding it back. That's a good indication that you might want to decompose to manage the complexity better and to move faster in certain parts of your tech stack. Also, if you are afraid to touch the code or if the deployments are really hurting and you don't really understand what is happening, also a good indication to decompose and to be more flexible in what you are doing and to reduce complexity in parts. If you feel locked into technology, taking the COBOL example again, and you can't use the best technology for the problems you want to solve, it's also a great indication to maybe carve out some parts and use better tooling to solve those problems. And lastly, that one is rather rare, but if your product really grows a lot in a short amount of time, if you go through a phase of hypergrowth, that's also an indication to really look towards this to make this more manageable and to grow and to support this growth. So I want to briefly talk about the Amazon story because that is really a success story of when microservices were the right call and worked out really well. So this goes back to the year 1994 when Amazon was founded. And from the beginning, it was a single monolith, it was an Oracle database, and then the business grew a lot. Like we went through a phase of hypergrowth and we grew in all dimensions, users, items we shipped, developers, and this led to a point where the business really was hurting because updates were taking a long time, features couldn't be delivered, and we needed to change something. And this then led to the famous, at least at Amazon famous, Bezos API mandate. So that was an email sent by Jeff Bezos where he essentially outlined that the company should do microservices. He didn't call it microservices at that time, but he really outlined the parameters. Systems that communicate via API, small teams that can be fed by 2 pizzas to build those APIs. Automate, you build it, you run it. All those things that we now consider normal for microservices have been introduced at Amazon in 2002 already, and that's how it is until today. So if we look at Amazon today, we have thousands of teams doing microservices, doing CI/CD, leaning heavily on serverless, and that leads to a really mind-boggling number of deployments that we see per year in the company. So now that we know why we want to do it and that we want to do it for the right reasons, let's talk about the how. And that's the Strangler pattern. That's one way to do it. So if we look back at our earlier monolithic architecture, Let's give it a name. Let's call it Storefront. And Storefront is a super successful global e-commerce company. And well, they are running on a monolith. They have a SQL database and all the things we discussed earlier. And that causes some problems in different dimensions. They suffer from low velocity, long release cycles. Features take a long while to be put in front of customers, and that is hurting. That is lost revenue, and you can't just compete with those new startups that are much more nimble in navigating their requirements. It also has operational inefficiencies, so it takes a lot of effort to just keep the thing running. And there's a lot of undifferentiated heavy lifting that the teams need to do to keep this thing afloat and make it work. And that not only has cost in terms of people that need to do this, but also has opportunity cost. If you need to spend time maintaining the monolith, you're not developing features. And lastly, Storefront operates in a regulated environment. So we handle payment data, customer data, and there are compliance programs we need to adhere to. And those are changing. And contrary to like features that come from the business side, this is not optional. We need to do this. So if we're not doing this, we get fined, we lose customer trust. That's a problem. So we want to change this. And well, we have a few requirements. Well, we want to go to market faster. We want to lower the total cost of ownership, so less operational overhead, more automation. We want to have higher performance, be better able to scale with our business, and we want to have better security and isolation by design. So what we could do is we could freeze the monolith to nothing and do a rewrite from the get-go and really write this entire thing new, design a new architecture. That does typically not work well. If your system is sufficiently complex that you want to rewrite it to microservices, there are in practice too many moving parts, too much complexity hidden somewhere, that if you attempt to do a big bang rewrite, you're doomed to fail. I have yet to see this to work out and have a happy ending. So there needs to be a better way. And in fact there is, and that is the Strangler pattern. It's sometimes also called the Strangler fig pattern because it is inspired by Mother Nature. And it's quite fascinating. The Strangler fig is a tree that when it grows, it wraps itself around another tree up to the very top, and it deprives the original tree of nutrition and of sunlight until the tree dies off, and it gradually replaces it, because all that remains is then the fig tree. And that's a very good analogy for what we are trying to do. We want to wrap things around the original tree until there's nothing left and we can just turn this thing off and let it die in peace. So from a 10,000 feet view, if we zoom out, this sounds rather easy. So we have our monolith, we lifted and shifted it, then we move out a microservice, we move out another microservice, and then we are done. All right, let's get coding, right? Let's do this. Not so fast. So this is really important. Before you write the first line of code, before you even touch the IDE, make sure you understand where you want to go. Make sure you understand your domain. You cannot make this up on the go. You need to have a clear picture where you want to go, and that requires a deep understanding of the domain and the problem you're trying to solve. And a tool that is almost essential to do this is domain-driven design. So entire books have been written about this, about domain-driven design. And if you want to do this, I really encourage you, read those books and apply what you learn from those books. They are an invaluable tool to help you on that journey. In a nutshell, what domain-driven design tries to do is it tries to map the entities you see in the real world, in your business, to the technological space. And it does so in creating what is called a bounded context. So a bounded context, the idea is to take those entities and group them into contexts where within one context you have a high cohesion, and between two contexts you have a loose coupling. So if you look at these lines between the boxes, you want to have as many lines as possible within one context and as few lines as possible between two contexts. And that then maps nicely to your microservices, because that is exactly what you want. You want to have little communication between those microservices and much in between. When it comes to defining those contexts, the most natural place to start is your business. Like, how does your business look like? And that is almost always the leading factor, but there are others. Technology. If you have different technology choices, that might factor into it. Location. If your teams are distributed across the globe, that might be a factor. Compliance might be a factor, or even the velocity that you want to see in the different parts of your microservice architecture. So really important to understand your domain and have a clear picture where you want to go and why you want to go there. All right, now that we've got all this out of the way, let's look at our monolith. So we've identified our domain, there's the inventory, there's an order, there's a card feature, and now we want to get going. We really want to bring this thing down. And the first place you should start is the user interface, if it has a user interface. If not, great, good for you. But most applications have some sort of user interface. And if you're lucky, you already decoupled this. You have some APIs on the back end and some web bundles that communicate with those APIs. If that's the case, again, you're lucky, just move them to some content delivery network and you have your first success. If not, invest some time to make it like that, to expose APIs and extract the front-end part. Because at the end of the day, the monolith is going to go away. You need to do this anyways, so best start with it. Once you've done that, the next thing you need is to introduce a proxy. So what the proxy does is it makes routing decisions, because at some point there will be requests that need to go to the monolith and there will be requests that need to go to the new microservices, and that's what the proxy is for. When we have the proxy, in the beginning all requests go to the monolith, but that's about to change. Another thing that is important, in an ideal world, you would like to freeze the monolith and not do any work on it while you strangle it. In practice, that is not happening. You can't explain this to your CPO. So if new features come in, really try to implement them in the new architecture. Really try to make them your first microservice. Because if you do it in a monolith, you're just delaying the problem. You're going to have to do this later on anyways. So in this case, now we want to have a recommendation feature for storefront. That is our first microservice. We built that, and that is routed to by the proxy. But now comes the real deal. Now we strangle the monolith. So we pick one of the features, in this case the inventory, take the code, move it to a microservice, have the proxy route to the microservice, and be done with it, right? Unfortunately, it's not that easy, because there are still dependencies within the code. The card feature requires the code of the inventory feature. Same goes for the order feature. And if we just remove those parts, we're going to crash. That's not going to work. So what we need to do is we need to introduce something that is called the anti-corruption layer, ACL. And the job of the anti-corruption layer is to provide inside the code the same interface to the dependencies of the piece we removed, and know how to direct those requests to the new microservice via the proxy. So from the point of view of, for instance, the order feature, nothing has changed. They connect to the inventory feature, that is just a stub that calls the ACL, and a response comes back with a higher latency because we're now going over the network, but in terms of interface, nothing has changed. And that's how you then make sure that you can remove bits from the code without breaking anything. We introduced another challenge. We have two data stores now. As I mentioned, the inventory microservice, that owns the data regarding to inventory. That's the principle of microservices. So now we have a problem, because the inventory microservice owns the data for inventory, but there might also be dependencies on data related to inventory in the existing monolith. What we could do is we could write from the microservice to the common monolithic database, but that's an anti-pattern you should avoid at all costs. So the solution to this is the so-called synchronization agent. And the synchronization agent has one responsibility, and that is to synchronize the data between the microservices and the existing monolith. The pattern that we apply here is called event sourcing. Some of you might heard of this already. And every write operation that goes to the inventory microservice is written to queue, an event bus, or whatever, and then picked up by the synchronization agent and put back into the monolithic database. Once we've done that, we can continue strangling the monolith. So now we pick the order service, remove it, make the ACL call again. The order has a dependency of inventory. Previously, this was a call in code. You just called some functions, some methods from within the code. Now, this is an API call. This is a fundamental part of microservice architecture that you now only communicate via APIs. There's no direct call to any database of another microservice. Again, we would apply the synchronization agent here. It's not in the diagram. And then we can continue. Now we can do the card microservice. We apply the same principles. We do the same thing. And once we've done that, removed all the complexity, all the functionality from the monolith, all the data resides within the data stores of the microservices, and we finally can turn this entire thing off. And we arrived at the final strangled state. And that is great. Now we have a microservice architecture. We still have the proxy in place, and that looks good. And we gained a lot. If we look at this from a bit of a different perspective, from a more technical perspective, we now can use different technologies. We can use different programming languages. We can use different compute services. It's all Lambda here, but this could also be containers or whatever. We can use different databases that are more suited to the specific workloads that, for instance, the order service needs. And that is a great thing. But as I mentioned in the beginning, we had to make some trade-offs. So we achieved our goals where we wanted to go, but what we traded off, or what we got in return, is that we now need to manage distributed complexity, which, as I said, is not an easy thing to do. Again, there have entire books been written about this, and I really recommend to read those if you deal with microservice architectures. They are fantastic books, and what they do is they give you tools and design patterns that will make this much easier, like patterns that have been battle tested in practice across many different architectures and proven to work. And I don't want to dive too deep into this, but I want to mention a few of the design patterns that I consider most important for you to know about when you approach such a journey of going to microservices. So the first one is the circuit breaker. And the circuit breaker is required in synchronous communication. So if your APIs call other APIs via HTTP calls mostly, that's when you need a circuit breaker, because it regulates the calls between the APIs. Because what otherwise can happen is you can have these cascading failures, like microservice A calls B, that calls C, and if C is having a bad day, suddenly you have like B not responding and A is depending on B, A not responding, and then what can happen is that one microservice can bring the entire thing down. That's not what you want. So use a circuit breaker pattern to handle this timeouts, this network congestion. That's a must-have essentially. Another view on a circuit breaker is a service mesh, which is mostly seen in container applications. It's a bit more than a circuit breaker. And the idea is that you decouple the communication from the actual application logic. So you have a sidecar container running next to your actual application, and the application communicates with that sidecar container, and then the sidecar container takes care of the communication via the network. It knows where the packets needs to go. Maybe there is some throttling that needs to happen. Maybe he needs to apply some circuit breaker logic, and that significantly increases the operational control you have over your distributed system. It's mostly done for containers, so if you're using containers, service mesh is certainly something worth looking into. An event-driven architecture, that's often the natural evolution of a microservice architecture. So if you come from a microservice architecture that you've built via the Strangler pattern, those tend to be synchronous in terms of communication in the beginning, because that's just like closer to the mental model of building a monolith. But over time, most microservice architectures evolve to being event-driven. And I don't want to dive too deep. There are some great talks on this very conference on this topic, but just be aware this is something that will likely happen and you should be equipped to handle this. The Saga pattern is important because when you have a complex system, you handle transactions. So that's just something that essentially every complex system does. If you buy an item online, you need to charge a credit card, you need to trigger the shipment, and so on and so forth. If you do this in a monolith, this is more or less a solved problem. You have ACID in the database, you have all the tools in the programming languages to handle errors. And those mechanisms, they mostly go away if you build a distributed system. So you need to find ways to handle this in your distributed system. And that is the Saga pattern. So in the Saga pattern, you define local transactions. You have an overarching orchestration layer that handles this. And if one of those transactions fails, all the local transactions get sort of reversed so that the entire transaction is also set back. If you're doing this on AWS, I recommend the service called AWS Step Functions, because at the end of the day, what you're building is a workflow. And that is exactly what Step Functions is really good at, modeling workflows in a cloud-native way with all the control logic for error handling and so on. There are a number of pre-defined patterns out there that you can reuse for your workload. And this is really a fantastic service if you need to implement the Saga pattern. Lastly, data management, we talked about this. You will come at a point where you might be tempted to sort of not be disciplined anymore, to just for this one feature, because it needs to ship real quickly, go to the database of a different service and violate the principle of no shared state. Do not do it. If you do it once, you're going to do it twice, and then you have essentially the worst of both worlds. You have what is sometimes called a distributed monolith, and that is not a pleasant place to be, because that is really a painful thing to maintain. Really stick to the principles, only communicate via well-defined APIs, REST APIs, message queues, never interact with the data that is owned by a different microservice. When you have distributed data, at some point this data needs to be brought together. If you have customers and they want to use your website or your app, you need to bring all the data together. And the pattern for this is called backend for frontend. So this is a dedicated layer in front of your microservices that knows how to get the data and just unify it and return it to the caller. And these days, GraphQL more or less is a de facto standard. So GraphQL is a fantastic tool that does exactly that. It solved the problem it was developed at Meta and solved the very problem at Meta, so it really at a large scale. It knows how to get data from different data sources, and you can send a query where you just tell the GraphQL resolver what data you want from what data source, and you're going to get this back in one query. If you want to get started with GraphQL on AWS, I really encourage you to look into AppSync, which is by far the easiest way to get started. It's serverless services. It's super easy to use. And it's a great tool to make the querying of data in a microservice architecture much easier for your clients. There's also the backend view. So you also need to bring the data together for things like reporting, auditing, BI. And there is another pattern for this, which has a really long name, CQS, the Command Query Responsibility Segregation Pattern. So I'm only going to repeat this once. It's quite a mouthful. And the idea is we apply the same pattern that we did when we had the synchronization agent. So we do event sourcing. Every change that is written to one microservice is persisted somewhere in some queue, often something like Kafka is used for this. And then you have an event store, and then you create a read data store, essentially, where you bring all this together. And that's where the name comes from, because you have your commands. So the write operations at the top, that's where the write goes. And you have unified read operations that give you a view on the entire data store by bringing those into the read database. It's an advanced pattern, but at some point, if your microservice architecture is sufficiently large, there is no real way around this if you want to have insights across all the data. All right, that brings us to the end, and I want to give you 4 key takeaways that I want you to take from this session. The first one, ask yourself why you want to do this, and then only to think about how you want to do this. This is really important. I think many attempts fail because they were done for the wrong reasons. Understand your domains. So have a clear picture of where you want to go, and that doesn't mean you can't adapt on the way, but start with a picture in mind where you want to end up. Don't make it up on the go. Use proven patterns to manage the complexity. You're going to have distributed complexity that is just inherent to microservices. That is one of the trade-offs you're going to make. And make sure to use established patterns to handle that complexity and not reinvent the wheel. And lastly, stay disciplined. The entire microservice thing, that will only really work out if you stick to the principles and remain disciplined of how you build the architecture and don't try to take shortcuts that will really hurt you in the long run. Thank you.
Sorry. Hi. Now we have a few questions in Slido. If I may read it to you.
Go ahead, please.
So, how do you make sure not to be totally depending on one supplier, for example, AWS? How to keep suppliers compete?
So that's something I hear quite often with customers, and the general fear is vendor lock-in. And the simple answer is there's a trade-off again you need to make. If you want to stay vendor neutral, you're not going to realize many of the advantages that the cloud has to offer. Then you're going to be stuck at what I showed earlier, the optimization stage. For some companies, that's a trade-off they want to make. But if you really want to maximize the benefits, you need to commit to some degree.
Then we have another one. You may see it on your screen as well.
Monolith are usually tightly coupled, transactional and sync. How do you deal with it while extracting microservices and all the distance problems? So this is in partly addressed by the anti-corruption layer. So what the anti-corruption layer is, it allows the communication to remain synchronous, but it adds latency. And that's something that you can't avoid. You can keep the latency low, but there is the network call, there's the marshalling of the data. That's something you need to account for. But other than that, going from a monolith to a synchronous microservice architecture has more or less the same mental model. The calls just take a bit longer. I would not recommend to try to go from a monolith directly to an asynchronous architecture that where you use some event bus, message broker, because that is just too many things you're trying to attempt at the same time. And then again, it comes down to patterns like circuit breaker, managing the complexity. But as I said, doing distributed things, that is really hard. And the moment you carve out one thing from the monolith, it becomes a distributed system.
Does this answer the question?
The monitor? Ah, okay. Yeah, that's great. Hi, so just separate DB for each microservice. Doesn't it lead to need of data duplicity? There might be microservices that don't need a database, but if the microservice by design has a certain task that it needs to solve, and most of the time you're going to need data for this, and then you should have a separate database. What is an absolute anti-pattern is shared state, because that leads to many problems down the road. So yes, again, it's about trade-offs, but that is one of the trade-offs you're going to make. Separate data store for each microservice if it needs to store data somewhere. A single common database between microservices is an anti-pattern. There are a few reasons. The most common one is how do you update schemas, for instance. So imagine you have a distributed microservice architecture. How do you control schema update if you think about SQL? That is one of the big reasons. When you have a monolith, you can do that quite easily. You update the schema, you update the monolith, you're done. If you're not doing this, then you lose all the advantages of microservices, because then you need to update the schema and you need to reflect that update in all the services that use the common database. There are others. I mentioned a book, Building Microservice Architectures. There's an entire chapter about this. I think you can even read it online for free, where the author goes into great depth, but that is just one of the most crucial ones, I believe. What is your take on Monolith, modular monolith as a first step before going all into microservices? That is a fantastic question, and that is a very good pattern. So, as I mentioned, it's a spectrum. You have microservices on the one end, that's the one extreme, then you have monolith on the other side. And there's in between, and in between is a modular monolith, and that can work really well. That's something I would encourage you, if you're a startup and you have high ambitions, don't start with a microservice architecture, start with a modular monolith. So a modular monolith is a monolith that is designed in a way that it can easily be separated. So you just don't write spaghetti code. You don't anyways, you're great developers, I know that. But don't do spaghetti code like in general. Write modules, but have them as part of one monolith, but be prepared to split it up. So yes, that is a first step you can take to make the strangling easier. And some way you're going to do this because you need to scope the code that you want to extract, and that can then be also considered a module. What if monolith to be decomposed is full of hopeless technical debt and dependencies, making it a complicated process? Maybe then a full rewrite makes sense. This thing is, when your code is that complicated, there are likely some edge cases hidden in the code that some smart developer implemented 15 years ago that are really crucial for your business, because they catch this one exception where, I don't know, a credit card number is a prime number. Just a silly example. And you're not going to catch that. And that's what I meant. If you start from scratch with all the good ambitions, but your business has like 30, 40 years of technical debt in itself, you need to reflect this at some point. And it's much easier to catch those edge cases when you gradually strangle this and you have like a reference how it is supposed to work. And then you can like do things like A/B. Some requests go to the monolith, other go to the microservice, and you see if they behave the same. That is really hard to do if you do a big bang. What is your opinion on using SOA architectural style instead of domain-driven design for finding bounding contexts, only applying domain-driven design principles for stuff inside bounded contexts? I mean, that's hard to answer. It's pretty similar, so I can't really give a good answer on that. It depends. That's the typical architect answer. So the architect is a great role to be, because you can always say it depends if you don't want to answer a question. If we want to restructure our code based on domain-driven design and move to microservice, should we move to microservice first and only then refactor? It's hard to separate those, because if you're at the place where you can just take the code and move it out of the monolith, you're already at a good place. You're at what's called a modular monolith that we had before. So there will be some refactoring in the process. Code base, should we move to microservice only then refactor? I mean, if you know they need to refactor and you can manage the complexity, it might make sense to start doing this in the monolith and refactor to a state where it makes it easier for you to extract. Because if you not only change the overall architecture from monolith to distributor, but also refactor the code, that's again a lot of moving parts. So if you feel you need to really refactor the code while doing the strangling, probably do it first and make sure that the monolith keeps working, and then take that refactored code and move it out.
And probably the last question.
You assume that domain is well understood. That is not always the case. How do you suggest to handle this? Yeah, that's a problem. If there's no one that understands the domain, that is a bad place to be. I would say tough luck, but what you can do, I mean, it's difficult. You need to speak to the business. That's the one thing. And other than that, it is trial and error. And the best you can do is like raise awareness that this is going to be a painful process. So you, as the owner of the refactoring, you need to be transparent, and you need to communicate to your stakeholders that this is really a difficult journey, and things will break, and this is not going to be fun for everyone involved. And the less you know about the domain, the harder it is to mitigate this, because then you are bound to run into those edge cases that no one can foresee. That is just a reality. Try to gather as many information as possible, but know that it might not be enough to avoid all the bad things that can happen in that scenario.
Okay, our time is up, so thank you, Markus, a lot.
Thanks for having me. Oh, thank you.
And I want to remind you that Markus, maybe at the Ask Me spot, if you didn't have a chance to ask your question, you can do that in person.
Yes.
Okay.
All right. Thanks.